Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of 2D geometry. As usual, before we enter the study of today's lecture, let me give you a quick review or overview about the answer to these 4 questions that you may have in mind. Question number 1, why to study this course? Question number 2, how to study this course? Question number 3, what are you going to learn from this course? Question number 4, how to learn the knowledge from this course. So let me start with the answer to this first question, which is about why to study this course. By now, you should know that our mission on Earth include number 1, to understand the world. Number 2, to improve the world. Then how to understand the world? The answer is to discover knowledge about the physical world through the use of sensory data. Then how to obtain sensory data? The answer is to make use of a measurement and the sensing system, right? Then how to improve the world? The answer is to invent smart products, smart machine, and the smart system by incorporating closed-loop feedback control system. Then what is a closed-loop feedback control system? The answer is it is a system which includes 3 basic building blocks or 3 basic building modules. One of them is a sensor, right? So therefore, this course is extremely important. For example, in future city, you may see the presence of a smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, and also Internet of Things. And you understand that the 2 basic devices inside Internet of Things include sensor, right? The second question that you may have in mind is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask yourself about these 4 questions. Question number 1, who are the user? Question number 2, what does it need from this user? Question number 3, what should be the functionality of the product or system that you are going to develop in order to meet the need of this user? Then question number 4, what should be the solution behind the design of your product or your system in terms of a sensor or Internet of a sensor, etc. Right? So the answer to question number 1 should be obvious to you because user include ourselves and smart product, smart system, and the smart machine. And the answer to the question number 2 should be obvious to you as well because all these users have the common need, which is to have sensory data, right? Then answer to question number 3 depends on the nature of the user. For example, smart vehicle may need to have a certain type of a sensor, and the smart robot may need to have another type of a sensor, right? The answer to question number 4 is to study well this course. At the end of the study of this course, you will know the solution behind the design of a sensor or Internet of a sensor, etc. All right. Then question number 3 is about what are you going to study in this course? Basically, this course will cover the study of the physical principle behind the popular sensor in electric domain, magnetic domain, environmental system, and the intelligence system. In addition, this course will give you the basic detail about the physical world, the basic detail about the conceptual world. Also, this course will teach you the basic knowledge for you to cope with randomness in the physical world and for you to understand fuzziness in the conceptual world. All right. And for you may have in mind about how to apply basically showing you that you are going to apply learned knowledge in order to guide the design of a sensor or Internet of a sensor, right? And the design of a sensor include these two basic steps. Step number one is to transform the value of a physical quantity on the measurement into readable value. And step number two is to calibrate your measurement and the sensing system so that the output will be exactly equal to the input, and the unit of a measurement assigned to the output will be the same to the unit of a measurement of physical quantity on the measurement. For the sensing element, or for step number one, in general, you may face these two situations. The first situation corresponds to the case in which it is good enough for you just to make use of front-end sensing element in order to transform the value of the physical quantity on the measurement into readable value. However, in most cases, you may face the second situation in which you have to use a series of at least two sensing elements in order to transform the value of the physical quantity on the measurement into readable value. Right, so this slide basically show you the guideline for you to follow in order to apply learned knowledge. All right, now we are ready to move on to study today's lecture, which is about the measurement of 2D geometry. So this lecture is an extension to the lecture on the measurement of a visual signal. In the lecture about the measurement of a visual signal, we just focus on the measurement of a photometric information. That means from image, immediately we will be able to obtain intensity knowledge and the color knowledge about the incoming light ray, okay? Received by the measurement and the sensing system, right? And in that lecture, you understand light ray has a starting point, has an end point. Okay, light ray will end into the receiver, and the light is emitted, okay, by light source or reflected by point in physical environment. So now we want to know, okay, from the perceived coordinate, for example, the index coordinate or image coordinate, all right, could we recover or compute the coordinate of a point in which the light ray has been emitted or reflected, right? So the answer is yes. Okay, so in this lecture, we are going to consider the special case in which all the point of emission of light ray are within a two-dimensional space. Then in this way, we should be able to determine the coordinate in this two-dimensional space from the image coordinate perceived by the sensor of visual signal, right? So that is the purpose of a study for this lecture. So you must consider this lecture is an extension to the lecture on the measurement of a visual signal, because the measurement of a visual signal include the measurement of intensity, color, and the geometry. Okay, then for this lecture, we focus on the measurement of a 2D geometry. Then another lecture will allow us to study the measurement of 3D geometry. Right? So try to make your mind clear about the purpose of doing study or measurement of 2D geometry. All right. So let's begin with the physics behind 2D geometry. All right. So under the context of measurement and the sensing system, and here we assume that the light rays are emitted from the point which remain within a two-dimensional space. Then how to determine the coordinate of this point from the perceived coordinate inside the digital image, right? So what of 2D geometry? The answer is our real life. There are many applications which require such measurement. For example, when we guide the vehicle to move on the road, actually we can consider the road surface to be a two-dimensional space. Or when we develop an autonomous boat or ship, okay, we can consider the water surface to be approximately a 2D space or two-dimensional space. All right. So here I'm going to show you two videos. So the first one is about the guidance on road. So we have a land vehicle which move on the road. Then we can consider the road surface to be a two-dimensional space. The second video showing you autonomous surface vehicle move on the water surface. Then we can consider water surface to be a two-dimensional space. All right. So there are many similar applications in real world. Therefore, it is very important for us to measure, okay, 2D geometry. All right. So before we look at the solution, for us to determine 2D geometry from image coordinates. So let's have a quick review or overview about the basic physics or mathematics behind 2D geometry. All right. So by definition, 2D geometry basically refers to the appearance of a physical quantity, physical entity in a two-dimensional space. All right. And what is a 2D space? A 2D space basically consists of a set of positions which are fully determined by two coordinates or with two reference axes. So we have an X coordinate and the Y coordinate. All right. So with the two coordinates, we should be able to fully determine the spatial location of the point in a two-dimensional space. All right. And the appearance of a physical quantity in the two-dimensional space is manifested in the form of a shape or 2D shape. Here you see we have a circle, triangle, square, star, rectangle, heart shape, closed shape, arrow, etc. All right. So this slide basically showing you the typical example of a shape or appearance within a two-dimensional space. And then in this case, we use the OXY coordinate system to provide the reference to this two-dimensional space. And in a two-dimensional space, actually, it is interesting for you to know that any complex shape could be considered as a combination of a set of primitive shape. Okay. For example, we can use these two functions to do the composition of complex shape. One function is a connect point at the angle, and second function is a connect curve at the offset. So with the combination of these two basic functions, eventually we should be able to produce or synthesize very complex shape in a two-dimensional space. And here I'm going to show you some example. For example, we have a straight line with one endpoint at the point A, and another straight line with one endpoint at the point B. Right? If let's say we apply this function connect at the point AB, okay, with an angle of 60 degrees, then here is a background knowledge. Right? We can consider shape as a rigid body, therefore we must assign a local coordinate system to each shape, right? So this is a coordinate system assigned to the straight line A. This is a coordinate system assigned to the straight line B. Then the angle basically means the angle between these two coordinate systems, right? So for example, this is the coordinate system of line B, this is the coordinate system of line A. So then the orientation or angular position, okay, or displacement, okay, between these two coordinate systems is 60 degrees, all right? So by applying this function, then we should be able to obtain this composite shape, right? And here is one more example, all right? So we have a straight line A and the curve B, and the curve B has a local coordinate system, and the straight line A has a local coordinate system. And now we connect them at the point A, point B with this angle, but pay attention, this angle means the angular displacement, okay, between these two local coordinate systems, right? So then you just look at the orientation between, or relative orientation between these two local coordinate systems should be 45 degrees, right? So then we should be able to produce this type of composite shape, right? And then if we apply this function, let's say we have a closed curve, okay, a 2D curve, all right? There's a C1, another triangle, it is a C2. The triangle is also a closed curve, right? So we can compose this composite shape, okay, by connecting them between line C1, C2 with offset D. Then in this case, we should be able to obtain such a composite shape, right? So basically, by combining these two functions, you should be able to synthesize all kinds of shape in a two-dimensional space, right? And this is the background knowledge for you to know, because in a two-dimensional space, actually with a discrete representation, or let's say inside the digital image, any curve could be approximated by a polyline, right? So if we have a closed curve, then we have a polygon, all right? So therefore, we want to know what should be the sum of inner angle inside the polygon. So this is the formula for you to know. I guess every one of us know that the sum of the inner angle from a triangle is 180 degrees. Now you know how come it is 180 degrees, because when n equal to 3, 3 minus 2 times 180 degrees is equal to 180 degrees. So basically, this is a formula which is applicable to any polygon with n number of edges, right? So this is the background knowledge for you to know in case if you want to know what should be the sum of inner angle of the polygon, all right? So besides the shape, we also need to know the position and the orientation of a physical entity in a two-dimensional space. For example, these are the mobile robot which could move on the table on a two-dimensional space. So therefore, this mobile robot will have traveling the location. Okay, the location include linear location and the angular location, right? So this will be the part of 2D geometry, right? So 2D geometry include not only the local shape, but also the global traveling the position, okay? And here is a typical example. Let's say in the vertical plane, we can consider vertical plane is a two-dimensional plane, right? When the object move, he will pass through a series of spatial location, right? Then in robotics, by definition, a series of spatial location without the time constraint are called as paths, right? So now you see this technical term, paths. For those of you with robotics knowledge, now is straightforward, all right? So you know what is paths. Paths refer to the spatial location without the time constraint, all right? And then you will see, let's say we have a 3 mobile robots, okay? At the time T0, they are here. At the time you go to 6 seconds, they are here. When T equal to 14, they are here. When T equal to 20, they are here, etc. So you will see once we know the spatial constraint, then we can include time constraint. Then in this way, we are able to control the motion of mobile robot or moving object in a two-dimensional space, all right? So therefore, besides the path, then we have another technical term, which is called trajectory, all right? For those of you with robotics knowledge, you should know this definition, all right? And here's one more example. Let's say we have this mobile robot with a two wheel. It's a bicycle-like mobile robot. So we can control the motion of these two wheels and let them to follow the same spatial location, or control the two wheels and let these two wheels to follow their own individual spatial location. So this is the second scenario, this is the first scenario, right? So therefore, you will see for the actual control of position, orientation of the object in a two-dimensional space, we need to have a time constraint, all right? Then spatial location with a time constraint are called as a trajectory, right? So this is the second technical term, okay? It's quite important for you to understand, all right? Then for example, when we drive a car, let's say this red car will bypass the slow moving white car. Then you will see, okay, what is the time function for its x coordinate? Let's say this is the x-axis, then this is the y-axis. Okay, so we need to know what is the time function for x coordinate and the time function for the y coordinate. All right. Once we have a time function, we can compute first order derivatives, second order derivatives, and the third order derivatives. So first order derivatives means what? Velocity, okay, in the x direction. This is the acceleration in the x direction, okay? And similarly, we can determine time function for y-axis, etc. Right? Then for articulated motion, there's an angular position. If let's say we have this humanoid robot, when this robot swing its arm, normally inside the arm, we have 6 joints. Then each joint must have an angular position. Then we need to know what is the time function for the angular position for each joint. Then in this case, we should have a 6 time function for a single arm. Then this robot has a 2 arm, 2 leg, and the finger and the body and the head, etc. So you will see, in order to determine the time function for this mobile robot, there's a lot of work, all right? And for each angular position, actually, there's a single variable. So it changes the angular position inside a plane. So actually, it is a 2-dimensional motion for each individual joint, right? Because there's a single angle, all right? So you move in a rotation plane, right? Okay. So that's about the basic knowledge behind the 2D shape or the basic physics, okay, about the 2D geometry, etc. Now we want to know, okay, what are the parameters of 2D geometry, all right? So from the study in the previous slide, immediately you understand that we need to have a parameter which describes the local shape, okay, triangle, circle, rectangle, whatever, plus global position and orientation. So immediately you understand, okay? So there are 2 types of parameters, all right? When we combine position, orientation together, and the result is called as a pose, all right? P-O-S-E. So therefore, there are 2 types of parameters. One is related to pose, and the second one is related to shape. And the study or description of the pose should be done within the global coordinate system. For example, in a 2-dimensional space, we have this global coordinate system, and inside we may have a multiple shape or multiple 2D geometry move around. For example, then for each individual entity, we can study its shape within its own local coordinate system. So you remember, for every rigid body, for every shape, we assign a local coordinate system. So from here you see, this is a local coordinate system assigned to this hard shape, right? And this is also local coordinate system assigned to this shape. And even with a single point, we can also assign a local coordinate system to it, right? So then in this case, the description of a shape occur inside local coordinate system, and the description of the pose occur inside the global coordinate system. Okay, so make your mind clear about the way to describe okay these two type of parameter. Now I'm going to show you some example, and then okay you will remember. Okay, for example, how to represent the position okay of a shape okay when you move within the global coordinate system. So we can use position vector, and actually this position vector refer to the origin of the local coordinate system, all right, with respect to the global coordinate system, all right. And another way is to have a function which constrain the x and the y coordinate together. And remember here, the xy coordinate refer to the xy coordinate of the origin of the local coordinate system. All right. So either we use a position vector or a function which constrain x and the y coordinate. So these are the two basic methods for us to describe the spatial location with respect to the global coordinate system. All right. Then if let's say we want to impose the time constraint and we want to know the time function for x, y coordinate plus theta, because there's a change of orientation. So in a two-dimensional space, we just need to have these three coordinates should be good enough. Okay, x, y plus orientation. All right, theta. All right. So then in this case, the good news is we can have an individual time function for x coordinate, for y coordinate, for theta, right? Then it is easier for us to handle because, for example, x coordinate is a polynomial equation of a time of a degree 3 or degree 2 or degree 1. Okay, so as a designer, we can choose a polynomial equation of a time, right? So that is quite straightforward for us to know how to describe the pose of a shape with respect, okay, to the global coordinate system. All right. Then here is an example for you to practice. For example, a mobile robot move in a two-dimensional space. When t equal to 1, the robot pass through this coordinate, and when t equal to 3, it pass through this coordinate. Then what are the time functions representing the coordinate of the origin of the local coordinate system assigned to the mobile robot? All right. So then in this case, we use a polynomial equation of a degree 1. Okay. So you have ax times t plus bx, right? So when t equal to 1, so then we know that the x coordinate is equal to 2, and the y coordinate is also equal to 2, right? Then when t equal to 3, the x coordinate is equal to 4, and the y coordinate equal to 7. So therefore, we have these two equations for us to determine ax, bx. Then these two equations for us to determine ay, by. All right. So these are the results. So therefore, the time function for x coordinate is this one. Time function for y coordinate is this one. So it's quite cool, right? Then how to represent the angular position of a 2D shape, okay, inside the global coordinate system. So then in this case, we just need to have a single angular position, for example, the theta, right? So there is a convention that by default, we can always imagine that the local coordinate system is aligned with the global coordinate system. When there's a rotation about the z-axis, about the axis which is perpendicular to xy plane, all right? So then we have this angle theta, okay? Once we have this angle theta, the unit vector of the local coordinate system, x and the y will be equal. Let's say for I, the unit vector of x will become cosine theta, sine theta. And this is unit vector for y axis become negative sine theta, cosine theta. If we put these two unit vectors together to form a matrix, so actually this is a rotation matrix, okay? So rotation matrix basically represent the orientation of the local coordinate system with respect to the global coordinate system, all right? So, and this orientation is achieved from time t0 to t. Okay, so this is a notation for you to know. All right. So actually, this rotation matrix basically represents the orientation of the local coordinate system with respect to the global coordinate system. All right. So then this is just a simple example. At the time t1, the rotated angle is θ1. At the time t2, rotated angle is θ2. Okay, so it's quite straightforward. All right. So that's about the representation of a position orientation of path and the trajectory of 2D entity with respect to the global coordinate system. Then how's about the description of the local shape with respect to the local coordinate system? All right. So then with respect to the local coordinate system, we may have a line type of shape. Then in this case, I guess every one of you know now, okay, what is the equation of a straight line? Okay, so y equal to ax plus b. That's it. All right. Okay, then here is an example for you to practice with this equation. For example, this line, okay, pass through coordinate 2, 3, coordinate 10, 8. Then what should be the equation of this line with respect to the local coordinate system? All right, so then you just choose any point x, y. Then you will see the ratio between displacement, okay, from xy to the starting point, okay, one end point, and should be equal to the increment of x coordinate and the increment of a y coordinate. All right, so proportionally, okay. So if you compute the ratio, so this is the increment of x coordinate, this is the increment of a y coordinate. If you just compute the ratio, this ratio will remain constant, right? Then what is the increment of y coordinate when you move from a 2, 3 to xy? That should be this one. Then what is the increment of x coordinate when you move from 2, 3 to xy? That is this one. Okay, so this ratio remain constant. All right, so you simplify it, then you should be able to get this equation. Then A coefficient is equal to this one, B coefficient equal to this one. Okay, so it's quite straightforward. Then this slide showing you some exercise for you to practice at the home. All right, so this should be quite simple exercise for you to do. Right. Then how's about the circle type of shape in the two-dimensional space? And I guess every one of you know now, okay, the equation of a circle at the location xc, yc with a radian r. So this is the equation now. Okay, so it's quite straightforward. So if let's say we give in this situation, what should be the center of the circle? What should be the radian of the circle? So immediately you know the center of the circle is -2, +2, right? Then radian is what? You count the number of the square, 1, 2, 3. Number of division, 1, 2, 3. So it's 3, radian is 3, all right? Okay. And here is an example for you to know how to use this measurement of a 2D geometry to undertake quality control for the geometry. For example, you have a machined part like this gear, okay? And we want to verify the dimension of outer circle, okay? And if let's say the measurement system tell you x1, y1, x2, y2, and x3, y3, and we want to know what is xc, yc, and what is a radian, all right? Then you can compare the measuring the parameter with the design specification in order to know whether this machined part conform to the design specification or not. So this is a typical example of making use of a measurement of a 2D geometry to undertake quality control for visual inspection, all right? So then in this case, since we have a 3 point here, which belong to the circle, then we have these 3 equations, okay? Because we can write down the equation of the circle and assume this circle pass through x1, y1, x2, y2, x3, y3. Then we have these 3 equations. So we can expand these 3 equations, okay? Then let the first equation minus the second. Then in this way, we will be able to remove xc square, okay? and remove YC square. So first one minus second one, then we have this equation. Then first one minus the third one, then we will have this equation, all right? Then we can rewrite these two equations into the matrix form, okay? Because we need to compute XC, YC. Then this is a 2 by 2 matrix. Then XC, YC equal to the inverse of this square matrix times this vector, all right? So once you know XC, YC, then you should be able to use any of these three equations to compute what should be the R, right? Then you can compare XC, YC, R with the design specification to see whether this part conform to the design specification or not. All right, so this is a typical example for you to know how to do visual inspection for quality control. All right. So we have the two-dimensional space. Then what should be the equation? Okay. For straight line, we have polynomial equation of degree 1. Then for circle, we have a polynomial equation of degree 2. Then for curve, the shape, you can use a polynomial equation of degree 3, 4, 5, etc. But there's a good news for you to know is any complex shape could be approximated by a series of line segments. For example, we can approximate this curve with 1, 2, 3, 4 line segments. Then for each line segment, it's easier because we know the equation, and each line segment has a 2 endpoints. So therefore, representation becomes extremely simple. All right. So that is a practice, okay, for us to know. All right. So in order to handle very complicated curve in the two-dimensional space. All right. So that's about the mathematics behind 2D geometry. Now we want to know, okay, how to measure this 2D geometry from visual signal, right? So you remember the previous lecture, we know, okay, with the camera, we are able to capture incoming ray and convert it into optical image, then convert optical image into analog image, then from analog image into digital image. And the digital image basically is a matrix of a pixel or matrix of a point. So therefore, at any particular point, okay, we know the index coordinate. Then the question is, for this index coordinate, what should be the corresponding object coordinate inside the two-dimensional space? If we know the solution, then straightforward for us to compute the XY coordinate in the two-dimensional space, right? Then we should be able to come out the result for the measurement of a 2D geometry. So this is a procedure for us to follow. Then you may want to know, why do we need to measure 2D geometries? The answer is there are many applications which require such information. For example, when we do inspection of a machined part, then we want to verify the geometry and to see whether the geometry is conform to the design specification or not. And also we may want to measure the location of a specific object in order to guide the robotic arm to do the pick and the place, all right? And for the driving of the vehicle, we want to know what is the relative position of the road with respect to our car. Then we know, okay, how to determine the steering angle and the driving speed, etc. Right? And also, when we read the text, okay, or read the report, so you see the printed character are 2D entity, right? So eventually, we want to do the cognition and the recognition, recognition of the character, for example, right? To support the reading by machine, because we can read the book, John. Okay, then maybe in future a robot can also read the book, okay, and convert the printed character into meaningful information. So therefore, okay, so 2D vision is very important for machine to obtain the necessary input, right? So these are the application, and this slide basically showing you more detail about the vehicle guidance. For example, we may want to know the relative position between the landmark and our vehicle. All right. Then in this way, we know whether our vehicle moving within the land or there is an offset shift to the left or shift to the right, then you can make a decision about the steering angle, something like that, all right? And then for pick and place, for example, we want to know that, okay, the position of the object in the two-dimensional space. For example, in this case, we only want to know XY coordinate. It's good enough. Then we guide the robot to do the pick and place, right? So these are the typical example for you to know. Then what should be the working principle for us to do the measurement? As I mentioned earlier, this lecture is extension to the lecture on the measurement of a visual signal, right? So in that lecture, we know, okay, we can capture incoming light from any space, all right? Now, in this case, assume the incoming light from the point on the two-dimensional space. So we treat all the point on the two-dimensional space as a light source, okay, as a point in which light ray will be emitted, right? Then all the light will be captured by the lens to form an optic image. Then image sensor will convert optic image into analog image. Then analog image could be transformed into time function of the voltage. Then time function of the voltage could pass through the microcontroller. So AD converter basically is a part of the microcontroller. Then after that, we have a digital image, right? Then inside the digital image, for whatever reason, let's say we know at the one particular point, we know the index coordinate, that's a row index, column index. Then we want to know what is the corresponding XY coordinate in a two-dimensional space, right? So this is a scenario for us to do the measurement of 2D geometry, right? So then in this case, we just want to know, because in previous lecture, we know the solution for us to transform incoming light into digital image. Therefore, our focus is on the solution which will transform index coordinate back to the XY coordinate, right? So, so this basically summarizes what we have studied in the lecture about the measurement and the sensing of a visual signal. So basically, inside the image, we have two types of information. One is geometric information, one is photometric information, right? And the geometric information is about the index coordinate of the image point or pixel, right? Now we want to know, okay, how to transform the index coordinate of the image point back to the XY coordinate in a two-dimensional space, all right? So image coordinate inside camera could be related to object coordinate in a two-dimensional space, okay? So that should be the focus of the study for this course, because for intensity color, immediately you know like at each location, you have RGB value, you can convert RGB into LAB or HSV or something like that, right? So we have a study all these transformation of color information, okay, in the lecture about the measurement and of visual signal. So now we focus on the computation of XY coordinate from index coordinate in the image space. Okay, so here I directly show you, I will go through the detail proof then for you to understand, okay, why is this so? So from this solution, immediately you understand it's quite straightforward, right? So input is index coordinate sensed by the image sensor, because inside the digital image, we know the color information. We also know the index coordinate, row number, column number, right? So then here, it's for a digital image, we use U to represent the column number, V represents the row number. So we have a UV index, right? So you remember in C programming language, row number, column number always start from 0. Then in MATLAB, always start from 1, all right? So that means 0, 0 correspond to this element, right? However, inside the image plane, we have a real image coordinate, X and the Y. So therefore, we have a second coordinate system for image plane, right? And on top of that, since for every rigid body, we must assign a coordinate system to it. Since we have a camera, this is why we need to assign a camera coordinate system to the camera. Okay, so here lays the background knowledge for you to know. Okay, so the origin of the camera's coordinate system is at the center of the lens, right? And the x-coordinate is x-axis is parallel to the x-axis of the image plane, and the y-axis is parallel to the y-axis of the image plane. And the z-axis is pointing outward, and the z-axis actually is the optical axis or principal axis of the lens, right? So because in the lecture on the measurement of a visual signal, we have studied the basic property of a lens channel. Okay, so this one is the center at the lens. Now you may ask this question, all right? So normally image plane is inside the camera. Now how come we draw the image plane at the symmetric position outside the camera? The answer is mathematically they are equivalent. The information are equivalent. And then it is easier for us to visualize, to understand the transformation when we draw the virtual image plane, which is in front of the lens, right? Because all the information inside this image plane is equivalent to the actual image plane, which is behind the lens and inside the camera. Okay, so this just for you to know, mathematically is strictly equivalent. Okay, and then in this way it will help us to understand or help us to simplify the description. For example, if let's say we have a point Q which will emit light ray, then this light ray will travel, because you remember during the lecture on the measurement of a visual signal. So when the light ray pass through the center of the lens, it will follow a straight line. There's no change of the direction. So since the center of the lens is the origin of the coordinate system assigned to the camera, so you just need to link this point, which will emit the light ray, to the origin of the camera's coordinate system. Then you draw a straight line. Then this straight line will intersect with the image plane. Then intersection actually is the image point. Okay, so then you can get the XY image, the real coordinate of the image, and the index coordinate of the image. All right, so that's it. So that is the background knowledge. So once we have an optic image, then we apply image sensor to obtain analog image, because here you will have the optic image, then analog image. After analog image, then we could be able to convert it into time function of a voltage, then pass it through the microcontroller. Then we have a digital image as the output. Then digital image basically is a two-dimensional point. All right, so this slide basically help you to do a quick revision about what you have studied from the lecture of measurement of a visual signal. All right, so now I'm going to show you the detailed step of the proof. All right, so first, we only interested in the two-dimensional space, and this because there are many applications which just requires information from a two-dimensional space. So for example, to pick up the object and place it on the conveyor. Okay, so then you see everywhere is a plane. Okay, so we just treat them as a two-dimensional space. All right, and then we use a single camera. So then we have a global coordinate system. Then for the camera, we must assign a coordinate system to the camera. The convention is the origin of the camera's coordinate system is at the center of the lens. The center of the lens is here, right? Then normally the real image plane is behind the lens. Then for the convenience of the description, we use the symmetric image plane, which is in front of the camera, in front of the lens, right? Then we have this virtual or equivalent image plane, right? In this equivalent image plane, we have a real coordinate system assigned to the image plane, okay? And after digitization, then the output is a matrix of a point. Then for the matrix of a point, we consider there's an index coordinate system. So you have column, you have a row, etc. Right? So these are the definition of the coordinate system. All right. So this is just to set up a 2D plan. Then we use a single camera. Okay, so we have a camera to observe the two-dimensional space. Right. Then for the camera, normally the image plane is inside. Right, and the camera has a range of observation from the bottom, the nearest plane to the furthest, okay, the distance. So you have a minimum distance to the camera and the maximum distance. So this is the observation range along the optical axis, right? So that is quite straightforward. So we put the camera there. Then we assign all these coordinate systems. So this is the global coordinate system assigned to the workspace, right? So here we assign a 3D coordinate system, okay? So this is for the convenience of description. And later on, we will consider z equal to 0, let's say, right? So then we have a camera coordinate system. Then this is an image plane, right? So this is an optical axis, right? So we have a 1 point here. Then the light ray, if we pass through the origin of the, or pass through the center of the lens, then you will follow a straight line. And this straight line will intersect with this image plane. Then you will see image point there, right? So now we want to know, if let's say we know the coordinate of the point with respect to the reference coordinate system. That means we know the x, y, z coordinate with respect to the reference coordinate system. Then what should be the coordinate of the same point with respect to the camera coordinate system, all right? So if we know the orientation of the reference coordinate system with respect to the camera coordinate system, if you see this notation, this means what? This is the orientation and the position of the reference coordinate system with respect to the camera coordinate system. So this you see, this is a unit vector for x for the x-axis, a unit vector for the y-axis, unit vector for the z-axis. Then this is the position vector of the origin of the reference coordinate system. All right. So for those of you, if you already forgotten the motion transformation, then you need to do a little bit of revision. Right. So this is the orientation of this reference coordinate system with respect to the camera coordinate system. This is the position vector of the origin of the reference coordinate system with respect to the camera, okay, coordinate system, right? Then you do this multiplication. So this is the XYZ coordinate with respect to the reference coordinate system. If you times this transformation matrix, then the result will be the XYZ coordinate of the same point with respect to the camera coordinate system, all right? So once we have an XYZ coordinate with respect to the camera coordinate system, then we can start to study the relationship between image point and object point within the camera coordinate system, all right? Otherwise, we cannot, because if let's say we only know the XYZ coordinate with respect to the reference coordinate system, then the image plane is with respect to the camera coordinate system. There's no relationship, John. So there is this transformation matrix, we'll link them together. So this is why we need to transform the XYZ coordinate from reference coordinate system to camera coordinate system. Okay, once they are within the same coordinate system, and it's easier for us to talk about the projection or the capture of light ray. So then within the camera coordinate system, the XYZ, now you see XYZ with respect to the camera coordinate system, will be projected into the image plane in this way. That means the X coordinate equal to the focal length, the X coordinate divided by Z coordinate within the camera coordinate system. And the Y coordinate of the image point is equal to F times Y coordinate divided by Z coordinate inside the camera coordinate system, all right? So then these two equations could be written in this matrix form, all right? So you can easily expand this matrix form to verify you can obtain these two equality, all right? Now you may want to know how to obtain these two equality within the camera coordinate system. So the next slide gives you the more detail, all right? So it's quite important to understand this slide, all right? So now you will see this is the camera coordinate system, and this is the image plane. Then this is the real image coordinate. And then if let's say you have a one point in a two-dimensional space, then this point will emit the light source or light ray. And this light ray will pass through the center of the lens by following a straight line. Then this line will intersect with the image plane. Then this will be the image point, PD, all right? So then you will see this triangle is similar to this big triangle. Therefore, then you see QP, QC divided by OOC. QP, QC divided by OOC should be equal to PW, QP, PW, QP divided by PD, O, PDO, right? Then this one divided by this one should be equal to the x coordinate of this one divided by x coordinate of this one, okay? And also is equal to the y coordinate of this one divided by y coordinate of this one. So x coordinate of this point is xw, and the x coordinate of this point is xd, and the y coordinate of this point is yw, and the y coordinate of this point is yd. So you have a bisymmetry of these two triangles, and you can get this ratio to be constant, all right? Then from this equality, then immediately you know that the x coordinate in image plane is equal to focal length times x coordinate divided by y coordinate in the camera coordinate system, all right? Then from this equality, then you know now, okay? And yd is equal to y coordinate divided by z coordinate times the focal length, right? So immediately you see this two equality, all right? So this is a result due to the projection of light ray emitted from point PW and in the direction which will pass through the center of a lens, which is the OC, and this light ray will intersect with the image plane at the point PD. That's it. Then we have this the symmetry between this triangle and this triangle. Then we have this ratio. All right. So this is a quite fundamental equation. So this one is quite important for you to understand. Okay, this is something new to you. Try to get used to this two relationship. All right. So once we have an optic image, now how to convert optic image into analog image. We have a study this one. I just replay back this video. So then we put the photodiode to convert the light into electric charge, and the electric charge could be shift down row by row, then one column, one row, shift out the column by column. All right. So row by row. So last row is they shift out the column by column. All right. Then reach the last one, then column by column shift out there. So this is a way to convert analog image into time function of the voltage. Then after that, we do the AD converter, then we obtain digital image, right? So basically is shift down row by row. After that, then it's column by column, sequentially shift out, right? Something like that. Then once we have a time function of the voltage, then we can send this into the microcontroller or dedicate the AD converter, right? So then we will obtain digital value row by row. Then we can pack all these row together to form this matrix. So you will see the index for row is start from 0 all the way to 479, and the column start from 0 all the way to 499 in C programming language. So it means what? The index coordinate, the origin is somewhere here at this column. So this is why we draw U, V in this way. Then now we have additional coordinate, that is the index coordinate. Then what is the relationship between XY coordinate or real image coordinate and the index image coordinate? So the answer is when XY equal to 0, that means the origin of real image coordinate system is at the row V0 and the column U0, all right? Then when there's an increase in X, then this X value will produce how many additional columns? The answer is X divided by the width of the column. Then when there's a Y coordinate, then what should be the increase or decrease of a row, okay? Then you just use Y divided by the height of the row. So immediately you have this relationship, all right? If they say now the X, Y are not equal to 0, if they are equal to 0, the index coordinate is quite straightforward, U0, V0, done already. If they say it's not equal to 0, you have X, Y here, then X will introduce extra column, okay? Then X divided by the width of column. Then Y will introduce extra row, then Y divided by the height of the row, okay? So then we have this relationship. Then good news is you can combine these two equations into this matrix form, all right? So you can expand this matrix equation to recover these two equality. Then you understand the transformation, all right? So I just write down the result, so it's true. Then how to understand these two relationships? I give you a slide for you to understand, all right? So, and you look behind the image plane. So you, UV is a digital image, and the XY is an analog image, right? So if X equal to 0, Y equal to 0, then the corresponding index for this point is U0, V0. If let's say now your image point has XY, for example, your object point is here, and you emit a line, the line is a pass through the center of the lens. This is the center of the lens, all right? Then you will intersect with this plane. Then if you produce XY, now XY is not equal to 0, then you just need to know that X will introduce how many columns, all right? So then X divided by the width of each column, then that means X divided by the width of each column. So that gives you the extra column, okay, with respect to U0, then you have this equality. Then for Y is the same. So now the Y is equal to this one. Then you just use this one to divide it by the height, okay? Because by default you have a V0. Then Y will introduce extra row. Extra row is equal to Y divided by the height of each row, right? So then you have this number of additional row. So then add them together, then should be the U correspond to this point. So you have a UV. So then these two equations can be written in this matrix form, all right? And from here, you will see both sides could time a scaling factor like S. It's no problem mathematically, it's equivalent, all right? Okay, this slide is also quite important for you to understand because this is something new, all right? So you understand the relationship among the geometry or between the coordinate, all right? Now we are ready to combine these three equations. This is what? This is to transform the coordinate of the object point from the reference coordinate system to the camera coordinate system, because we will do the study inside the camera, all right? So transform it into the camera coordinate system, all right? And then what is this equation? So this is a formation of optic image, because when the object point emit a light ray, when it pass through the center of the lens, then it will follow a straight line. This is a straight line will hit the image plane at the location. That location has a coordinate, that is an XY coordinate, all right? So this is a relationship between XYZ coordinate with respect to the camera coordinate system and the real image coordinate inside the image plane. Then this is what? This is a digitization, because the analog image will be digitized into a digital image. Then for the digital image, because digital image is the final output from the measurement of a visual signal, because we only know the UV, all right? Then we want to know the relationship between the real image coordinate and the index image coordinate, all right? So we know this relationship because it's a digitization, row by row, column by column, all right? Then you will see we can put these three together, okay? Start from here, both sides times S. Okay, then you have SX, XY, S. Then replace this, substitute this one by this result. Okay, then we have XC, YC, ZC. Replace this one by this result. Okay, done already. Then combine them together. Then we can relate UV to XYZ with respect to the global coordinate system. Okay, so when this one times this one times this one, so actually result is a 3×4 matrix. Okay, so because this is a constant, so it's because this is a 4×4, John. This is a 3×4. Then this is 3×3, so end up like a 3×4. Okay, something like that. All right. So then this is very important. This is the equation of a camera's forward projection, because in the next lecture on the measurement of a 3D geometry, we will use this equation. All right. So this is why this lecture basically also prepare you to study next lecture, which is about the measurement of a 3D geometry. All right, we will use this equation. All right, just pay attention to this equation. Now for this lecture, because we only focus on the XY coordinate in a two-dimensional space, so it means what? Z coordinate actually is equal to 0. All right, then once you put the 0 here, means what? You can remove the third row. After removing one row, then B matrix become a 3×3 matrix. All right. So this one relate XY coordinate to UV, and here our problem is reversed, because we know UV. We want to calculate XY, but the good news is what? This is a square matrix. We can compute the inverse. Right. Then we calculate the inverse. Then we can relate XY to UV. So it means if we know the UV times this one, we can compute XY. Done already. Now you see, we know the solution. Then this is a 3×3 matrix, because the inverse of a 3×3 matrix is also a 3×3 matrix. All right. So this one we call it is a camera's forward projection. Forward projection means if you know the XY coordinate of the object point, then how to determine image point. Okay, you use this equation. Now our situation to do the measurement is reversed, because we know the image. We want to measure what is XY. So we will use inverse projection, all right? Because we know the UV, okay? The sensor tell us the UV index coordinate. Then we want to know what should be the XY coordinate, okay? So to do the measurement, we need the inverse projection equation, all right? So then done already. So now you see we have this solution, okay? So finally, we prove this solution, all right? So then once you know the implementation of this principle, then always remember to do calibration. And here you will see, actually, this already give you the calibration equation. You must calibrate with this equation, okay? Then how to do calibration basically means what? You just give the XY coordinate in the 2D plan. Then, okay, you will see, obtain this is a index coordinate from the image plan. Then in this case, the YI correspond to the UV. Then from the UV, you determine this projection matrix, okay? This projection matrix, all right, this one. Then after that, you can calculate ZI. In this case, the ZI correspond to this vector, right? So remember to do the calibration. Then how to do the calibration. So this slide help you to understand, right? So basically, if let's say you have a 2D geometry like this rectangle placed in front of your camera, basically one XI. So SI is a set of coordinate for the vertex or vertex, right? So you have for this rectangle, so you have 4 vertices, right? So then you know the XY coordinate of this one, XY coordinate of this one, XY coordinate of this one, XY coordinate of this one. So these this set of 4 coordinate basically means that you have this input XI, all right? Then you capture image. Then this rectangle will appear inside image plane. Then you get a set of UV, 4 UV coordinate. The UV coordinate basically correspond to YI here, all right? Now you need to determine the calibration equation. Calibration equation corresponds to this matrix here. Is this equation, right? So, and with 1 point, let's say 1 object coordinate. So actually you have a 2 equation. Then with 4, then you have A, okay, equation. So then it is just enough for you to determine you have a 1, 2, 3, 4, 5, 6, 7, 8. Because here you have an A and no. You just need to have an A equation. Because for 1 point here, you just substitute inside here. Because for 1 point here, you know is UV, you know his XY. Then you put them inside this equation, expand it, you get the 2 condition already. 2 point will give you 4 condition. 4 point will give you A condition. With this A condition, you have a linear equation for you to determine this A and no, A, B, C, D, E, F, G, H. Okay, so it's good enough. Then you compute the inverse of this matrix. Then you use a programmer to do the matrix inverse. Okay, because to inverse A by A matrix is quite tedious by hand. So you must use a program or use MATLAB to do it. All right. So then in this way, you will have this equation here. Okay. After calibration, your measurement system is ready. That means you put any object here, you will know the UV. Once you know the UV, then you just use the calibration equation to calculate the XY. Then output here will be calculated the object coordinate. All right. So this is the object coordinate on the measurement. This is the index image coordinate output from the digital image. Then this is the calculated object coordinate from this measurement and the sensing system. Right. So try to this diagram with this okay. The setup of a measurement and the sensing system of a 2D geometry, then try to interpret correctly what is xi here, what is yi here, what is zi here. Okay, try not to be confused with x, y, z. Don't interpret it in this way. So this is just treat as an input to your measurement and the sensing system. This is the output from your measurement and the sensing system. This is the intermediate value of your measurement and the sensing system. Then in this case, for the measurement of a 2D geometry, this is the object coordinate as an input. This one is the index image coordinate, all right? Then this is a calculated object coordinate. That's it, all right? So after calibration, you can also do the error analysis. So after calibration, you put you can verify if there's I put the 1 point very precisely at the specific location. Then you calculate, you do repeated computation of measurement. Then you have measured the object coordinate. Then you can calculate mean value, standard deviation, right? And also you can move, let's say, this object coordinate from low, because you have an image, let's say, from the raw number of a low value to the raw number of a high value, or from a raw number of a high value back to the raw number of a low value. So you have these 2 sets of measurement. Then you to see whether there's an error gap or not. If there's a gap, then you have a hysteresis error. If there's no gap, there's no hysteresis error, right? So you can do error analysis with this measurement and the sensing system for 2D geometry. All right. Okay. So remember to do error analysis. Okay. So that's all for the study of this lecture. So key takeaway from this lecture is for you to know the basic physics behind 2D geometry and also the basic mathematics behind the description of a 2D geometry. And in particular, we know the solution which relate the index image coordinate to object coordinate in a 2-dimensional space. So we have an exact solution, right? So that's all for the today's study. Thank you for your attention, and I'm looking forward to seeing you in the study of next lecture.